So hi everyone, I am Navonil Saha from IISER Kolkata, and today I will be presenting my summer project talk on star formation in the multiverse. And I have been mentored by, supervised by Professor Lucas Lombreser and Dr. Daniele Sorini. So I will first give a brief outline of the whole talk. So first, I will talk a bit about the star formation model which we are using in this. Next, we will talk about the star formation rate density comparisons between these models. And then I will talk about some of the results and discussions part. And then at last, I will talk about the limitations of the model and the conclusions. So let's start. So talking about the star formation model. So as we know that the cosmic star formation rate is one of the key components used to describe and understand the evolution of galaxies, as we know. So apart from our own universe, which govern the standard cosmological cases, we also try to study the cosmological models that differ from our own in the value of one or more cosmological parameters. That can be the matter density parameter, dark energy density parameter, baryon density parameter, etc. So what is the main goal of this talk is to compare two different models, that is the star formation rate density comparison of the Busolike model, which has been given in 2009, and the recent 2021 Sorini-Peacock model. So let's get started. Yeah, so coming to the Busolike model. So as you can see from the first equation, so Busolike model has an approximation assumption that it can be applied to open, flat, and closed FRW universes. And this first equation shows the SFRD density equation. Now, the time T equivalent at which the matter and radiation have equal density is given by this equation, second equation, that is mu pi square by 15 T equivalent to the power 4, where capital T equivalent is the temperature equality. So, and the new parameter is taken to be 1.681. These are all taken from the BL model. Now, the temperature equality is taken to be 0.22 psi, where psi is the matter mass per photon, and it has a value of 0.82 electron volt. Now, the total density and pressure, the total density is given by the summation of the radiation density, the matter density, and the dark energy density. And the pressure is given as follows: rho r by 3 minus rho lambda. The cosmological perturbations are useful, specified by a time-dependent power spectrum, and the RMS fluctuation amplitude is the sigma, where r is the radius, and smoothing the power spectrum, we get the value of this sigma square, that is given in this equation as 1 by 2 pi square 3 sine kr minus 3 kr cos kr by kr cube whole square, and the power spectrum that's integrated from 0 to infinity. Now we then define this equation sigma m of t, which is a function of mass and time. So that is qsm into g of t. So where q is the amplitude of the primordial density perturbations, and sm is the fitting formula which the BL model uses. Now from this thing, we get the linear growth function g of t, which is a differential equation, as you can see. And we can, by solving this, we can find the linear growth function g of t. Now, the BL model uses the extended preceptor EPS formalism, so to estimate the halo mass function and the distribution of halo gases. So halo ages. So and the equation which governs this is given here by F. And now here the delta C, which is this thing, and this is approximately equal to 1.68, and that is the critical fluctuation for collapse. Now, as again pointed out in the first slide, so the star formation rate is given as follows: rho of t, and as you can see, The normalized SFR will be given by rho star of from integrated from 0 to T naught, and it is equal to FP into rho m by 10. Now here rho naught is the reference density. Now for the usefulness of the comparison between the two model, we comparison from the non-standard cosmologies, we parameterize certain things, and these are given as follows. So we first determine the cosmological parameters for an arbitrary flat lambda serium model with respect to the cosmological parameters of our universe, that is the standard cosmological case, and which acts as a reference cosmological model for both the BL and SP model. Now we use the CMB temperature as a marker for the time, and hence in the universe, in any universe today, is defined as the time when the CMB temperature is equal to the value observed in our universe, and this value is given by T naught is equal to 2.7255 Kelvin. Now at early times, the lambda serium universes are mainly radiation dominated. So for that case, we considered a sufficiently high redshift Zi such that the universe is well into the radiation dominated era. And at Z is equal to Zi, we get this get the density parameters as reference density parameters as the radiation density parameters is approximately 1, and the dark energy and the matter density parameters as epsilon lambda and epsilon m, where the epsilon m and epsilon lambda is less than 1. Now from this thing, we get the rescale the dark energy and the matter density by some constant alpha lambda and alpha m, and that will be the parameters which we will actually change for comparing different cosmological cases. And this is given as omega lambda is equal to alpha lambda into epsilon lambda. And as you can see that from the previous slide, that omega epsilon m is equal to the omega lambda reference. So from this equation, we can clearly see that the omega lambda in the new cosmology is equal to alpha lambda into omega lambda reference. And the omega m is also given as similarly. The omega radiation is equal to 1 minus alpha lambda into epsilon lambda, and that is approximately equal to 1. Now, in our universe, for the standard cosmological case, the alpha m and the alpha lambda parameter is taken to be 1. And now at the redshift of Z is equal to Zi, the Hubble constant will have the same value in all the universes. For different universes, we consider a scale factor A in terms of the Hubble constant, and that is given as Hi is equal to H of A of I, and that the formula is given as follows: HA square is equal to HI square minus, as you can see. And in the reference cosmology, we get the Hubble constant formula as H naught square reference into the radiation density, the matter, the density parameter, radiation density parameter, and the matter density parameter, and the dark energy density parameter. The Hubble constant in the new cosmology, in terms of the parameters of the reference cosmology, is given as follows: HA square is equal to H naught square reference, and the other and the summation as follows. Now, for the A is equal to 1 case, so we have the expression for the present day Hubble constant, which is given as follows. And so the evaluation of the Hubble constant in the universe in terms of the new cosmological parameters will be HA square is equal to H naught square into lambda the matter density, radiation matter density A to the power minus 4 plus matter density A to the power minus 3 plus the dark energy matter density. And the ratio of them is given as the ratio of the density parameters as given as follows. Now from this, we can, taking into the flatness condition, the expression for the cosmological parameters in the universe can be given as follows. That is omega radiation is equal to omega radiation reference by the omega radiation reference plus alpha m omega lambda reference plus alpha lambda and into alpha lambda reference. And the omega m and the omega lambda can also be followed as similarly. Now, after this, we take into account another parameters that is sigma 8, and that can be calculated numerically. So using the CMB code in the online Lambda tool provided, and we get the expression that we get the expression for the baryon density omega b as Fb into omega matter density, and Fb is given as alpha b into Fb reference. The primordial power spectrum amplitude is given as a capital AS is equal to alpha AS and into AS reference. And the sigma 8 parameter is given as alpha sigma into alpha sigma 8 reference, sigma 8 reference. Now we vary the sigma alpha sigma parameter by taking into account the density parameters, and after putting this density parameters value in the online Lambda tool for a certain set of cosmological parameters, we get the sigma 8 values. Now, keeping the alpha sigma value to be constant as 1, we change the sigma 8 reference value so that the alpha sigma value keeps takes the value of 1. So now after this, both the BL and SP model are consistent with the Planck 2018 cosmological results. And for that reason, we here have stated all the parameters, initial parameters, which we have taken for the reference model. So as you can see, the radiation density parameters and the matter density parameters, the dark energy density parameter, baryon density parameter, the Hubble constant, and AS and NS, and the effective number of relativistic roughness, degree of freedoms. So all these parameters are given as follows in the table. Next, we come to the star formation density comparisons. So we first developed the SFRD for our own universe, or the so-called standard cosmology, and then we start to vary the cosmological parameters one by one to investigate how the SFRD changes in this different universe with respect to our cosmology or our universe. We will take into account mainly 4 parameters for the comparison of the different cosmologies. They are mainly alpha m, alpha b, alpha lambda, and alpha s. And these are, as you can see from the previous slides, these are mainly dependent upon the density parameters. We can also say that we also change the sigma 8 parameters, as I told, which is dependent upon the alpha sigma. Now, in the case of standard cosmology or our universe, all the sigmas, all the alphas are taken to be 1, as I have also mentioned in one of the previous slide. Now, we gradually change this parameter one by one in the case of different cosmology cases comparisons. Now, both the BL and SP models are compared along with the original Hendricke-Springel model. And I should mention here that the SP model is an extended formalism of the Hendricke-Springel model that was given in 2003. And along with that, we also give the 2014 Maddow-Dickinson fit in the plot, as I will show you in the next slide. The plots are made mainly between the redshift in units of Z+1 in the x-axis and the SFRD in the units of solar masses per year per megaparsec cube in the y-axis. Now, we also, in addition to this, we also took equation 6 to 8 of Lombriser Smyer-Barreto paper. And here, the parameters which were given was the normalized inner and the outer functional behaviors, which is given as F in and F out. And so as you can see, and the expression of WZ is also there, and WZ is basically the kind of a weighting function, and the Z parameter, which is given as 1 plus Z inflection, as you can see, and where Z inflection is the inflection redshift. Now, coming to the comparison case. So for the first, we look at the standard cosmological case, and then we go on to the different cosmological cases. So for the standard cosmology, as I have said, all the alphas are taken to be 1. That is alpha m is equal to 1, alpha lambda 1, alpha beta 1, and alpha s is equal to 1. Now in this graph, as you can see that the red curve is given, the red curve is the Busolike in our code, and the green curve is the fiducial parameters of the Sorini-Peacock model, and the blue curve is the original Henriques-Mingle model 2003, and the black curve is the Sorini-Peacock best fit parameters, and the Maddow-Dickinson fit is actually almost coinciding with the equations 6 to 8 of the LSB paper, as you can see. So this is for the standard cosmological cases. I will come to the conclusion part at the end of the talk. Now, coming to this model, this graph, this plot. So here in this plot, what I did was I have in the y-axis, I have taken the ratio of the ratio of the SFRD to a standard SFRD of the Maddow-Dickinson fit. So it's basically the ratio of the SFRD to the SFRD of the Maddow-Dickinson fit as a standard model. So from this, we can see that the green curve is the Sorini-Peacock model and the red curve is the Busolike model. And this is also in accordance with the, this plot is also in accordance with the plots which is given in the 2021 SP model paper, Sorini-Peacock paper. Now, after this one, we come to the different cosmological cases. Now, for the different cosmological cases, we mainly vary two parameters, that is alpha lambda and alpha b. So that is basically the dark energy density, which is related to the dark energy density parameter and the baryon density parameter. So in the case of alpha lambda, we vary the alpha lambda three times. So keeping all the other alphas to be constant. So as you can see from the plot, so the first plot here shows the alpha lambda. So here I have taken we have taken the alpha m, alpha b, and alpha s to be 1 for all the cases, and we have varied the alpha lambda. So in the first curve, as you can see, so the first curve signifies the alpha lambda is equal to 0.1, then alpha lambda is equal to 10, and then alpha lambda is equal to 100. And the case and the alpha lambda is equal to 1 case I have already shown, which is the standard cosmological case. So the upper plots is basically the normal SFRD peak, SFRD plot, and the lower plots are basically the log-log plot. Now, coming to the different cosmological case of alpha b. So here also I have varied 3 parameters of alpha b, and here all the other parameters are alpha m is equal to 1, alpha s is equal to 1, and alpha lambda is equal to 0. So here I have varied the alpha b to be from 3, 1, and 0.1. So as you can see, and again, say as I said that the upper plots is basically the peaks, and the lower plots is basically the log-log plot of the peaks, SFRD peaks. Now here in this table, as you can see, so basically I have given all the combinations that I have taken for all the models, including the standard cosmological case. So as you can see that here we have, as I said, that we have taken the 4 parameters, that is alpha m, alpha lambda, alpha b, and alpha s. So in the first 4 columns, I have varied the alpha lambda, as I have said, including the standard cosmological case, and the next 3 columns I have shown the alpha varying of the alpha b case, and the BL SFRD peak, the SP SFRD peak, and the BL redshift peak and the SPZ redshift peak have all been given in the data here in the table. Now next, what I did was I have compared the SFRD peak for different values of alpha lambda using the data which I already showed. So in the first plot, as you can see, So here I have done a normal plot. So this is rho peak versus different values of alpha lambda, keeping the other alpha lambdas to be constant for all the models, for all the comparisons. So here, what I have taken is, so alpha peak versus alpha lambda for 5 different values of alpha lambda. So that is 0, 0.1, 1, 10, and 100. And all the other alphas are taken to be 1, that is alpha M, alpha B, and alpha S are taken to be 1. So here, as you can see, that we have got 5 points, as I have showed. And in the right side plot, what I have done is I have taken the log plot in the x-axis. Same case, just with the log plot. Now, after this, what I have done is I have compared the difference ratio. So here, what I have done is I have compiled the one point I missed is that, as you can see in the right plot, the log plot. So here we have got only the 4 points, as because the log of 0 is equal to minus infinity. So that is extending, 1 point is extending, the alpha lambda 0 value is extending towards infinity, minus infinity. So that's why we have got 4 points for the log plot. Now next we come to this plot, which is the rho peak SP minus rho peak BL by rho peak BL, this plot. And here also we have taken like 5 values, that is 5 values for alpha lambda, 0, 0.1, 1, 10, and 100. And all the other alphas are taken to be 1. I will come to the conclusion part at the end. Now, after this, what I have done is I have also compared the Z peak for the different values of alpha lambda. Here also, as you can see, the plots in the left side is basically the normal plot, and the right side plot is basically the log plot, the normal plot with the x-axis in log scale. So here also the log of 0 is equivalent to minus infinity, and hence we have got only 4 points, as the log of 0 point extends towards the infinity, minus infinity. For this case also, I have compared the ZSP peak minus ZBL peak by ZBL peak, and for the 5 different values, as I have shown, I have given. Now next we come to the comparison of Z peak for different values of alpha B. The previous one was alpha lambda, and now we are comparing the different values of alpha B. And in this case, I have taken 3 values, that is 0.1, 1, and 3. And the alpha lambda value is taken to be 0, and alpha M and alpha S value is taken to be 1. Again, the left plot is the normal plot, and the right plot is the log plot, in the log in the x-axis plot. And this one is the ZSP peak minus ZBL peak by ZBL peak versus alpha B for these 3 different values. Now we come to the results and discussion part. So I will start from the standard cosmological case only. So in the standard cosmological case for our universe, the BL model at intermediate redshift is in good agreement with the data. Although when we go to higher redshift, the BL model as well, both the BL model as well as the SP model, both seems to be slightly off with respect to the Henriques-Pingel model. The BL model might be off because of the crudeness as well as different modeling. As the BL model, like it is not a completely analytical model, as we have seen. So once the structure formation starts, the SFRD of the BL model rises rapidly and soon hits the peak, both in the case of our universe as well as for the different cosmological case. Now, the peak of the BL model occurs earlier, as we have seen, and the late time slope of the SFRD is also quite reasonable. Although in the case of SP model, the late time slope is not steep like the BL model. The SFRD in the BL model falls faster than the SP model, but the SP model, on the other hand, provide a peak of star formation, which is in better agreement with the data. In comparison with the HS model, both the models show similar results, and the peak of the SFRD occurs in the range of the redshift between 2 to 4. Thus, in other words, it improves the HS model where the peaks usually occurs at more higher redshift of 5 to 6. Now, what are the other things? For the different cosmological case, the BL model tends to show a higher value of SFRD as compared to the SP model, although the peak in the BL model occurs at higher redshift as compared to the SP model. The slope at a low redshift or the late time is more steep in the BL model, as also shown in the standard cosmological case. Now, from the comparison plots between the rho peak versus alpha lambda, we can see that the higher values of the alpha lambda, the SFRD peaks of both the model show very small difference and try to converge, as I have shown in this plot. Now, on the other hand, the comparison of the Z peak versus alpha lambda, we can see that the Z peaks of both the models show very large difference, and they try to diverge on increasing the value of alpha lambda. So as you can see in this plot. So this is Z peak versus alpha lambda. Now, so these were the main conclusions from the outcomes of the plots. Now, BL model obviously has some limitations. So I have tried to state all some of those. First of all, the BL model cuts off the star formation at lower redshifts. So it can't compute the SFRD for very low redshift values, supposedly close to 0. And that is also shown in the in the different cosmological plots, as I have shown for alpha lambda and alpha beta. The modeling of the SFRD tends to be crudely distributed when we try to compare different cosmological models in the BL model with varying cosmological parameters other than the standard cosmology. And the BL model also does not provide a detailed analytical fit to simulations or observation of the SFRD in our universe, as compared to analytical models like the Henriques-Pringle model, or maybe the SP model to some extent. The SFRD comparison in the negative redshift regions can't be computed using this model, as I have pointed out in the first point also. And hence we are unable to compare the negative SFRD comparison of the BL model with that of the SP model. The SFRD curve often starts to oscillate randomly in the lower redshift region when we change the cosmological parameters as compared to the standard cosmology of our universe. And this may result in spurious results in the calculation of the SFRD and the redshift peak from the plots. So as you can see that if I can show that in the lower redshift part, often the model tends to oscillate, and thus giving some spurious results when we try to calculate the SFRD or the Z peaks. Now coming to the last point, the SP model, the BL models also neglect the feedback effects from newly formed stars and the active galactic nuclei. So these were some of the limitations of the model, and thus we can conclude that the BL model has some limitations, as I have said in this talk, and we further need to improve this model for better comparisons. Some of the references which I have used in this talk and in this project are the following, and yeah, and thank you.
Okay, well, thanks. Anyway, I think the first question I've got is, in your conclusions, you said a few times, you talked about the crudeness of the Busolike model, I guess also compared to the Henriques-Pringle model. What do you exactly mean with the crudeness? In what aspect is, in your opinion, the Busolike model more crude?
So in my opinion, what the BL model says is that it does not give a complete analytical fit or the complete analytical fit to the star formation data. But what it does is that using the BL model, we can vary the parameters more in orders of magnitude. Because in the Henriques-Pringle model, it is approximately the variation of the parameters which we can do, as stated in the BL paper, is approximately 10%. But here in the BL model, what we can do is like we can vary the parameters to a greater extent in orders of magnitude. But like as I said in the first point, that it does not perfectly it does not give a perfectly analytical fit to the data. So that's what I mean by the crudeness of the model. In that case, you can say the HS model, the Henriques-Pringle model is better. But again, the Henriques-Pringle model falters when taking into account the varying the parameters more.
I see, but okay, sorry, yeah. There is another question, I see, but
okay, so my question is on the thing that you mentioned at some point, F in and F out. I haven't seen that before. Could you just expand a bit on what these are?
Yeah. So
yes,
basically, exactly. So basically, this, if you can review the Lucas Lumbriser and the Smear-Barreto paper. So these are basically some of the equations which they have given. So basically, what they have done is that the F in is the like normalized inner functional behaviors, and the F out is the outer behavior. And I don't know. I mean, they have given like they have tried to fit it with the Maddow-Dickinson fit, as I have shown in this plot. Yeah. So basically, the equation 6 to 8 of the LSB paper almost accurately fits with the Maddow-Dickinson 2014 fit. And I completely don't know what are the exact implications of all these equations. But like what I can say is from this that it has certain implications with the Maddow-Dickinson fit compared to the Maddow-Dickinson fit.
It was kind of a hypothesis on how it should look like.
Yeah. So maybe just to add on this point, it's more a hypothesis based on some cosmological coincidences.
I remember now.
Would need a certain behavior for star formation, and this is kind of the inner slope and the outer slope, or of the star formation rate, and it happens. It is not fit to Maddow and Dickinson. It happens to match it very well. Okay, there's a transition, of course, that you need to calibrate in that sense. But the slopes themselves are not, right? They are predicted essentially by this coincidence. If you want to have a coincidence. Okay. I also have a question actually maybe both for Navonil and Daniele. Is if you go to slide 21.
Okay, slide.
So
this one.
It is. It's very interesting to see that in with the change of alpha B, both the Busolike and the Serini-Peacock models behave very similarly.
Yes, exactly.
Which is maybe a bit surprising because baryonic prescriptions in Daniele's paper are much more sophisticated, right, than in Busolike.
So I was also surprised because in the alpha lambda model I see a difference, but I saw considerable difference. But in the alpha B, I saw that it is comparatively similar to each other.
Yeah, I'm not sure yet why you've got such a small difference in the position of the peak. However, to be honest, I'm not sure if I fully trust the results from Busolike and our code in this particular case at present, because as you showed earlier, alpha B equals 3.
Basically that was the main point which I wanted to show, is that when we compared this, so that here comes the crudeness thing. So also the oscillation thing which I was telling, that in case of the alpha B, so as you can see that the model is very crude. Like in the lower redshift part, if you can see for the alpha B 0.1 case, so it just stops abruptly. And for the alpha B1 case also, like it is oscillatory. So I don't know, it is like we have very good results with it, but I mean, these are what it is. But yeah, the BL model, so that's why, because of the oscillation thing, so the BL model oscillates, and thus I don't know that if we are getting the right redshift, the peaks might be wrong. But
well,
like,
I think in this case, the alpha b equal 0.1 is the one that looks more problematic. So the other 2 points are probably more reliable, and we should.
The other 2 points are probably more reliable. Yeah.
And nevertheless, since you mentioned the limitations of the Busolike and our model, including this one, for example, do you think that this sort of limitation is mostly numerical or physical? And what would you do? What are your ideas for the future to try and address these limitations?
Okay. So what I see from here is that it is mainly maybe numerical. So we can improve this model to lower redshift. And if we can do that, then we will get more sophisticated plots. Like I have seen your paper also. In your paper, we have got like you have done some comparisons in the lower redshift part also. So if we can do that, we can extend the PL model to lower redshift using the numerical changes. Then we can have a more sophisticated comparison between your model and our PL model.
Sorry, with low redshift, I presume you mean negative redshift in this case?
Yeah, exactly, negative redshift. Yeah, that's what I told in the last part. Yeah.
Okay, so and if sorry, Luis, but if I just may throw one more thing here, I think that, yeah, it's still interesting to see that, yeah, so the redshift of the peak seems to be very similar in both my model and Busolike and ours one.
Yeah.
But the amplitude seems to be
different,
pretty different, which, or that I'm not surprised, and it could be precisely because what you and also Lucas were mentioning earlier of the like more explicit feedback implementation that I try to include in my model. So it seems more a matter of how the star formation density evolves. So I guess we should probably look at how, you know, we transition between different star formation regimes. Like in our model, it's limited by the gas consumption time scale, high redshift, and cooling time scale, lower redshift. So maybe there's the transition between these two modes is the key. But yeah, I'm not sure. We have to think about that.
Yeah, we have to see for that. But yeah, the redshift part which you told is pretty similar, as I can see. The amplitudes are different. The SFRD amplitudes are different, but the redshift are almost similar, very close.
If I can comment on that, I think you're doing it on Mathematica, right?
Yeah, I'm doing it on the Mathematica.
So I think it's actually a numerical problem because I ported the code to Julia, so another programming language, and I don't have those problems. I don't have those instabilities. So there are two problems. Like I think numerically it's unstable, and also if you try to integrate very close to the, because you know in this formula for rho of t, you have an integral from t min to t max, and t max is usually the same. So you have a lot of intervals, and usually you have to integrate to t max. And if you get too close to a certain time, then you get then it's the results get very different, basically. So that could be a part of the problem.
Yeah, that could be a possible reason.